So in chapter 3-1, we start learning about solving for systems of equations. So far we've been dealing with an equation at a time pretty much, other than, with the step piecewise functions and so on. But now we're going to be dealing with a linear equation, possibly quadratic, etc. But it's going to be trying to solve uh, not just one, but two or three or four, etc. So we probably won't do that many, but for sure one or two equations, definitely three equations possibly at a time. So a system of equations are two or more equations with the same variables. So in other words, it doesn't mean that they all have x and then another x, and they have x and y, or they could have three variables, x, y, z, and so on. So a system is called consistent if it has at least one solution. So in other words, these two lines have a point in common, so they touch, right? So they intersect. So that's called one solution, and you call it consistent. But if a system of equations, so like two equations, are inconsistent, then they have no solutions. And I'm hoping you can picture in your mind two equations that don't have a solution. In other words, they don't touch. For example, parallel lines. There is no solution, and that's why they are called inconsistent. A system that is independent, it has exactly one solution. So what does that mean? Well, two lines that intersect at one point, and there they are. So these are consistent and also independent. So because they touch, they intersect, and they have one solution. Next, also a system can be dependent if it has many, many solutions. See, so one equation depends on the other. I know it looks like there's only one line here, but picture the line on top of another line, right? And so a line on top of this line, well, they're the exact same line. It just maybe looked a little different, and so you didn't recognize it until you actually do the graph. So that would be called consistent and dependent if it's a line on a line. So you're going to end up with, three possible scenarios. 2, 3, 4, 5, whatever many lines that they give you, they touch once, or they touch so many times that it's just infinite. You can't really give it a number because it's just infinity, right? So a line on top of a line, so it's practically the same line. Or you have no solution. They're inconsistent. You have parallel lines. Parallel lines, of course, as you know, never touch. So that would be a situation where you have some inconsistent lines. Pardon my cat. This is Wedo. He came to say hello. All right. So how can you solve a system of equations? I know some of you are like, well, Miss, I don't have a calculator at home. That's okay. You can still, you're going to learn about at least 4 different methods. So hopefully that'll help you solve these. So I created this little acronym here, GEMS, to help you remember the 4 ways that you can use to solve a system of equations. So a system of equations can be solved by graphing them. Just graph the 2 pictures and see what they look like, or look at a table. And hopefully you'll be able to see if there is a point that they have in common, they have no points in common, or they have all the points in common, right? Then you can also use elimination. So you try to get rid of one of the variables of one of the equations, and then substitute in and kind of get rid of the other, solve for the other variable. So you can do this when they both have the same coefficient. So like if the number, let's say you have an equation 3x plus 5y equals to whatever, and then you have another one that's 3x minus 7y equals to, well, there, 3x and 3x. Those are easy to eliminate because I could easily multiply the second equation by a -1. 3x minus 3x cancels, and you go on and do the rest. So, but we'll look at examples in a bit. And of course, we have matrices. That's one of the sections. I won't say too much about this, but it is a section we're going to go over a little bit later. And so a matrix, yes, like the movie, The Matrix, or the movies, right? It's kind of the same, when you just saw random green numbers kind of, falling. Well, in this case, they're not going to be random. We're going to organize them in a certain way, but it's called the matrix. So you build a matrix, and you can use a calculator, this function called row reduced echelon form. I will show you that on the Inspire in case you do have one. If not, like I said, once you come back to school, you can use the ones that we have available for you. And then there's the substitution method as well. So if you notice, there's 4 methods we're going to be looking at. So in substitution, you solve one equation for one of the variables by substituting into it, right? And then we'll look at those examples as well. So that is basically the preliminary information. This is these are notes here for section 3.2, but this is the stuff we're going to be dealing with right now, and then we'll go on to your packet. So in your packet for system of equations, we have section 3-1. On the first slide, slide 11, you see the vocabulary words that we've gone over pretty much in the notes, and then you have some examples and stuff. So it starts asking you to solve the system by completing a table. So that's just something you have to do. So just go ahead and either plug in numbers. So when try, the different things or solve for one of the equations and then substitute in the other, etc. So just, different things that you can try. It does show you here the table. So it tells you to do a table, right? So then it shows you how you do that. So the solution to the system is here. Now, what I'm going to do is I'm going to show you the steps on a calculator, how you can go ahead and enter a system of equations. But I'll do that later once we get to the next sections when it does say to, use a matrix to solve these. So for right now, go ahead and just do what it asks so you can practice. So it's saying now to graph. So you have to turn these into equations that are easy to graph. Turn the standard form that they gave you into the slope-intercept form. So y equals mx plus b. And that way graph the two equations, see where they touch or they don't touch, or it's the same line on top of each other, right? So they touch, many times. So it's an infinite number of solutions. So you're looking for one solution, no solution, or many solutions, infinite. All right, so then you can also graph, and it shows you here how to do that, substituting points. And then, of course, continue with the next examples, because all it is really you need to practice the methods. And so that way it would make it easier for you to see what is going on. If you notice here, it's asking you to classify this, and I gave you some definitions of ways to do that. Plus, also here, you have the examples that are in your notes if you copied the Cornell notes. So you'll be able to see which ones are consistent, independent, dependent, inconsistent, etc., like we discussed earlier. So again, take notes of anything important, like the substitution method. It gives you the steps to follow. So that's something that you might want to try as well. And then, of course, there's some more examples, and just why do you have so many different methods, right? Why would I use a table? Why would I graph the systems? When would I do a substitution? Well, it gives you little hints here, and you're going to notice the more you practice with these, the more you'll start seeing, oh, I should have done a substitution because I see this, or oh, maybe the matrix is going to be better because of this, and so on. So in your study guide, it does give you ways, ideas for solving them graphically and so on. So you can go ahead and start doing that, and that's it. Just graph the lines and see, if there is any intersection. And of course, it's going to ask you to tell them what kind, if you do find a system that intersects, are they considered consistent, dependent, considered independent, inconsistent, etc. So let me go ahead and look at one of these. And let's just take number 1, for example. The thing is, you have to turn it into the slope-intercept form. So if I move my 3x this way, and see, the more you practice these, it can become easier for you to do this. So this becomes y equals, I always like to have my mx, my slope first, and then the b value next. For the next equation, I know my 6x belongs over here, so I do minus 6x, and so therefore I have 2y equals to this stuff. I'm already going to divide the 2 for both sides. That way I have the y by itself, and see, the more you practice these, you can get a little bit faster at it. 10 divided by 2 is 5. However, I'm going to place it here since that's my y-intercept. It's just a constant, a number. And here I have the x, so I'm going to go ahead and do that. So negative 6 divided by 2 is negative 3x, and that was a positive 5. So those are my two equations. Automatically, I'm not even going to continue. Do you all notice something here? So in this case, I see that they have the exact same slope. So these two lines are parallel. So now knowing that, let me just graph them real quick. One goes through negative 2. This is your y-intercept, so negative 2. One crosses at 5, so it's 1, 2, 3, 4, way up here. And the slope is negative 3 over 1, so I can use this one down 3, 1, 2, 3 over 1, down 3 over 1. So if this is my line here, then the other one, and sorry, it's really hard with the pen that I'm using on my computer screen to do these, but I think you can see where I'm going with this. This is an actual, I think it's supposed to go a little more, like, shoot, sorry, I'm trying to make it better and I think I'm making it worse. But anyway, the point is that they're parallel lines. So now you can go back and answer, remember, what are parallel lines? From my notes, we could always go back and let me see if I can get that. So parallel lines, we already said that those are inconsistent, and you can look at the rest of the stuff there. So basically, you're going to be taking some of these graphs and just kind of figure out what's happening, and that way you can answer the questions that they give you. And then, of course, it goes on with a little bit more problems, but you have to decide, you know, well, should I do a graph? Do I do a table? Should I just do a substitution of some kind, and so on? So that just takes a little bit of practice. You'll start seeing hopefully some pattern. Now, let me give you a little hint. If you look at this question right here, question 4, this one right here, I already know one line. If you go back to an earlier session where I told you about Hoy and Bucks, this is a complete Hoy situation where you have y equal to 1, so it's a horizontal line going through 1. So there, that one was easy. And now, if I know that y is 1, can't I substitute it here? So if I do that, 1 minus what number is equal to positive 3? So we can move this over here. It becomes a negative 1. Negative x is equal to 2. So positive x is equal to negative 2. Because I can multiply this whole thing by negative 1, and that cancels that, becomes an x, and so on. So that I just substituted. So notice how substitution in this particular case would work for me, because then I can solve these. Let me just graph this one right here. Y minus x is equal to 3. Remember, move your x this way, it becomes a plus x. So y equals positive x plus 3. So let me just graph that line real quick so I can demonstrate how the substitution helped me. So this is an imaginary 1 here that you don't see, so you turn it into a fraction for the slope. So this line is going to cross at 3. 1, 2, 3. That's your y-intercept. And this is your slope. I rise 1, I run 1. Rise 1, run 1. Rise 1, run 1. So this is pretty much my equal. Let me try not to mess it up too much. So it looks like they're going to cross at this point. Well, if you noticed, when I substituted, what did I get? I got x is negative 2, and the y was a 1. So when you substitute, you get that point of intersection. X is negative 2, y is 1. So there's a method that you could have used other than the graphing. So I kind of used a combination, right? I graphed them, but then I had substituted just to show that you can find the answer. As long as both of the equations that you're using use the same points, then you're fine. Because that's the whole point of this. You're trying to find the one solution, if there is one, where both of those equations have the same point in common. And then you have a potential story problem that you can work on as well.